All right, now we are at 10:32 a.m. and we're gonna start. So everyone, good morning. And today we're gonna continue to talk about symmetric crypto. So if you still remember last time, we talked about the DES encryption, right? We talked about the cipher of DES. We talked about the very interesting history, and then we talked about Feistel network. And we mentioned that this nice property of Feistel network, which is that given a one-way function, and you can come up with another compound operation, which is called a Feistel computation. And you can make this one-way function actually inversible. Although a one-way function itself, it cannot be reversed. You can add a like one more layer, so it's like a compound function using this one-way function, and then you can do this inversal operation, which you can use for encryption and decryption. So this is the Feistel network that I'm showing right here. So you can consider that the first one, the first row, is the encryption network. I'm going to write over here. This is for encryption. And this part is for decryption. So given a plain text, it's going to be cut into half. So we say the right-hand side of this half plain text contains n bits, and actually it has 28 bits. Sorry, actually it's 32. And the other half also have 32 bits. And then for this half, let's just iterate one round. So looking at this part. So R0 will go to L1, and then another R0 will go to F1. So first of all, we have L1 is equal to R0. And then the other part of R0 will go to F1. So it will have F1 of R0. And then it's going to be XORed with L0. And it comes to R1. So R1 is equal to L0 plus the F1 of R0. And similarly, we're going to do this again into 16 rounds. And we get the ciphertext. And then similarly, to decrypt from a ciphertext to a plain text, you do similar operation, and then you will finally get the plain text. And last time, I remember a student was asking, like, in this case, then how are we going to involve key? Because after all, this is a crypto system, and we want to have a key comes into play. So here's the way that key can come into play. We define this one-way function as a function that is related to a key and x. So x in this case, if this is encryption, then f is R0, R1, R2, etc. So here, ki is the key for each round. Remember that we have 60 rounds, and originally the key is 56 bits. So the way that it works is that it will use a key expansion algorithm to expand the key from one key of 56 bits to 16 keys with 48 bits. Okay, so I'm gonna just write this formally over here so that it's gonna be easier for you to recognize. It is a key expansion. So from one key Well, actually, this is very informal. It's not a formal way, but I hope this also will help you to understand. So it will convert from one key with 56-bit to 16 keys, and each key has 48 bits. Okay. And then given this key, it will do this calculation. So it will come this into here. You will use this so-called Feistel function, which is a one-way function that takes key and R0, like the X as input, and it will output a value. And this value is also a value of 32 bits. Okay, so now let's take a look at Feistel function, which is this part. So the Feistel function, as I said, it is a combination. It combines the key and a 32-bit string. Well, I wouldn't say it's string. It's just like 32 a block, right? So here, what it does is that it will first have half block, which is this X, and the subkey, which is KI. And then the first we'll do an expansion on the half block, because later on we want to do an XOR. And before we do XOR, we need to make sure that the number of bits for each of the operators here is the same. So we want to make sure that after this expansion, E of X contains also 48 bits. And then the subkey also has 48 bits. So here is 48 bits, and here is also 48 bits. And that will enable us to do XOR, exclusive OR. And after that, there will be a substitution box. There will be a substitution operation. We also call this as box, which I will talk about that later. So after this substitution, what it does is that it will substitute some of the bits, change that to another value according to like a dictionary, a code book. This code book will tell you that if you have this value, then you want to substitute that to the other value. And then like if this value happens in this particular position, then you want to substitute this value to another value. And you see here, there are 8 bits. There are 8 boxes, and each box takes 6 bits as an input. And this is why if you count like each box here, you see that we have 6 lines, 6 arrows. So each box takes 6 arrows, and then it will output 4. So after this substitution operation, the input of the substitution has 48 bits, but then the output will be 8 boxes. Each box has 4 bits. You want to check over here. And that is equal to 32 bits, right? And in this way, after this permutation, we will also get a 32 bits result. All right, so this is the Feistel function. And then, as I said, we're going to talk about SBox. So this is very interesting. Let's take a look at SBox. What does a SBox look like? Here, I'm showing you an example. So SBox is about, as I said, like substitution some of the bits so that you can get the other bits. So SBox, it takes a 4-bit value as an input, a 6-bit value, and an output 4-bit, right? So in this case, this is an example of SBox, and this is S5. And the way that you check the X box is that you first check the first 2 bits, 0, 1, and then you check the last 4 bits, which in this case is 1101. So suppose that we're looking at this. So then we write this together. The 6-bit input is 0, 1, 1101. And then by looking at the table that we know that we want to substitute it to 1001. So this is the way that we change this 6 bits to 4 bits. And the tables, the box is called S box. Excuse me. All right. So now let's continue, but just keep in mind that this S box exists, and I will talk about some interesting things about S box later. Thank you for blessing me. Okay, so then, all right.
A question.
Yes, please.
Can you go back to that other slide just for clarification?
Yes.
It says outer bits, so we're really just taking the first bit and the last bit to decide the row, right?
Well, no, you actually take both this, as you said, this is outer bits, right? As well as this. So consider that, oh, sorry, actually, I get it wrong. So this is outer bit, and this is the middle 4 bits. So it's not this, sorry. So it is out bit, and then the middle. So it's gonna be 1101.
Okay.
Yep. And thanks for the clarification, Stephen. And also thanks, Dean. I just saw your message. This is correct. Yes, very nice catch.
Is there any significance to the S5 in the top corner? Did you go over that already?
No, I mean, I'm just taking S5 as an example. There's also S1, 2, 3, 4, 8, and 2, 8. So they all different though. And actually, yes. And then actually those S box, they are hard coded. So it's not gonna be changed. Everyone knows about this S box. This is like a public, this is part of the encryption scheme. And Emma was asking, what does the P box do? What the P box do, that's a good question, is that it does a permutation. Basically, it changed the order of this output 32-bit. I'm not gonna show exactly what the P box looks like, but usually it looks like as a matrix. It will tell you that if you have a 32-bit value, you're gonna put maybe the first bit to maybe the 13th bit instead. You want to change some positions, so you basically change the order. That's why it's called permutation. Okay, and Dylan says that he misses the first couple minutes about S box, and that's okay. So very quick, just a very quick recap for what S box is. S box is just like a table to tell you how to substitute, how to change from 6 bits to 4 bits. And then if you look at this Feistel function here, so for Feistel function, what it does is that this X box is an operation in the middle that converts 6 bits to 4 bits so that it will be able to do the latter operations such as permutation. All right, now let's continue. And by the way, guys, this is good. I like you guys asking questions by voice or by text. And I really like the way that we are interacting right now. So if you have more questions, and also thank you for correcting me. If you also find something that I just said wrong, please stand out and let me know. Great. So back to this like a very high level, or say like the global picture, looking at decryption procedure. So we just finished talking about this part, right? Which is called a Feistel function. And now let's look at this part, which is the key expansion part. So we just said that given one key, with a bit of 56, key expansion will convert that to 16 keys. And those 16 keys, each of the key has 48 bits. So how does it work? I'm not going to give you the exact details, but I'm going to just give you a high-level procedure of how it works. And you don't have to know the details. But if you are interested in it, you can just like search online. There is documentation, or even Wikipedia pages contain some of those contents. And in fact, those pictures they're coming from, like this picture, it's coming from Wikipedia. Okay, so for key scheduling, this is also called key scheduling. So the way that it works is that given the key, and we just mentioned this is 64 bits, it will first do the permutation. It will select 56 bits from the 64 bits. And then after that, it will rotate to, and then use 24 bits from each half. So it's like you first select 56 bits from the 64 bits. So here it's gonna have only 56 bits. And then it's divided into two. So here is 28. Other is also 28 bits. And it do some rotation, some combination, and it only selects 24 bits from each half, this bar. So it's like 20 half over here, 24 half, 24 from this half, 24 from the right-hand side half, and then they combine them together, it gets one subkey. And after that, it will keep moving. And again, every time it's gonna select 24 bits from the 28 bits, and then combine them together to get a second subkey. So this operation is kind of fixed, but the nice thing is that such rotation will make sure that approximately every bit is going to be used for 14 over 16 subkeys. So the key idea for this PC permuted choice is that we hope that every bit has been used in a approximately, or so like hopefully ideally slightly in an even chance. So every bit will have a similar chance to be used among all those 16 subkeys. So we want to be evenly distributed those bits so that will be used. And then there's no bit that is like never used or like very little time to be used, or there's a bit that has been frequently used. So this is the way that the key scheduling work. And back to the S box, there is a very interesting story. So as I just mentioned, that S box is hard-coded, right? So in terms of S box, actually, the initial version of this hard-coded S box is different from the final S box that is like currently used. Let me remove these. So according to one of the designers of DS, alien called Kong-Kim, I hope that I pronounced his last name correctly. So he says that we sent the S box off to the Washington, but they came back and were all different. So the NBS, when they revise this encryption scheme, they change the content of S box. And actually the way that they change is that it make it simpler. They make it contains digest less bits. So, and this comes into some concerns and some discussion when this happens in 1990. So in 1990, there are some researchers discover differential cryptanalysis. So this is a specific way that you can crack a crypto system. And people start to look into DES, look into DES, look into the S boxes. And they want to ask this question: are those S boxes resistant to differential cryptanalysis? And it turns out, and which is also fortunate, or maybe it's not really just because of luck. So the S boxes of DS was very much more resistant to the attack than any other kinds of AS boxes if it's chosen. So it seems that this AS boxes, when it's come back to the designer, has been well crafted enough so that it will be resistant to differential cryptanalysis, which is something that is discovered in the future. So see that the time, if you look at the timeline, let me just go back very quickly. Here, right? So this is the time that NBS asks for proposals and look into this option of DAS and decides to adopt DAS, right? So remember, this is 1966. 19 to be precise, it's 1976. So it's from 1973 to 1976, okay? But then if you look at this timeline over here for ASBox, it's very interesting because differential analysis is actually discovered in 1990, which is far more later than the time that people are looking into the DAS crypto. So there's a rumor saying that actually in 1970s, so that is the time that actually before the discussion of DAS, actually both IBM and NSA likely already know about differential cryptanalysis, but they were classified. So they didn't announce to the world that about this existence of such attack because they don't want bad people to take advantage of it. And then when the design does, they make it very delicate so that it will be resistant to this differential cryptanalysis, this type of attack that has been discovered by IBM and NSA back before. So later on in 1990s, another group of researchers, they rediscover differential analysis. And now it comes to the plate, coming to a public discussion about differential cryptanalysis versus DAS boxes. And it turns out it's good. The AS box is still resistant, so we can still use it. So this is a very interesting background. Rumors, or maybe not rumors, who knows, but something fun that I'd like to share with you guys. Okay, so far we talked about the design of DAS cipher, and I want you to think about how to attack DAS if it's possible. And since I already talked about this, I guess you already know the answer is yes, it is possible to attack DAS, but how to do it? And before you really use your brain, brainstorm the attack, let me just give you a scope of the attack. I would call it attack model. And I will tell you that what you know and what you don't know about the cipher so that you can start to think about how you can come up with an attack. So let's suppose that you know, or let me just go to this picture first. So you're the person, Eve, and you're in the middle of the communication of Alice and Bob. You know that Alice and Bob, they are using DAS. So you know the cipher that they're using, which is DAS, which is DES cipher. Okay. And because of that, you know the encryption decryption algorithm. Like you know exactly the design of DAS, which is exactly that I just showed you, right? You even know those AS boxes, you know the Feistel network, you know the entire encryption and the decryption algorithm. However, you don't know the key. So although you know the key expansion function, you know how that works, but you don't know the argument. You don't know the key itself. However, on the other hand, the good thing is that since you're evil, you are monitoring the public channel between Alice and Bob, so you can get a lot of plain text and ciphertext. Suppose that you know the plain text, okay? So just like suppose that you have this this crypto system with the key as a black box, and you will be able to get the ciphertext and plain text pairs. So you know that for some of the plain text, this is the ciphertext. Although you cannot choose which plain text you want to encrypt. So basically, you can think that you are a passive person in the middle, although you know the plain text that Alice is gonna decrypt and send to Bob. You cannot control Alice for what plain text that she's gonna generate and she's gonna send to Bob, but you know both of the plain text and the ciphertext. Okay, and then the goal for you is to infer the key based on ciphertext plain text pairs. And usually we call this types of attack a known plain text attack, meaning that you know the pairs of plain text and ciphertext, although you cannot choose it. That you know the pairs, but you cannot choose which plain text that you want to decrypt, you want to encrypt. You can also not choose which ciphertext that you want to decrypt, but you passively know some pairs. And your job is to infer the private key, which is like also the public key, because this is metric crypto. So your goal is to infer the key based on those pairs. All right, now I'm gonna give you some time to think about how to crack this specific cipher. And it's okay that you cannot come up with this entire attack like end to end, but if you have any ideas, feel free to share in the chat and I can tell you whether or not you're in the right direction. So Tanya said, brute force, check all the keys. And yes, that's the right direction. Keep thinking. And meanwhile, I'm also responding some of the message in the chat. So Tanner, your thought is definitely right. So that key space is small enough to check, so you can somehow brute force it. Great. So if you already have a concrete attack in your mind, Tanner, then I want you to think about the time complexity. And one of you are proposing finding the inverse of the Feistel function. I mean, that is part of assumption, which is that Feistel function is composed of this one-way function, and we assume that reversing the one-way function is like theoretically or computationally impossible. So basically, you won't be able to inverse the Feistel function efficiently. Physically go and attack Bob. That is a brilliant idea. Please make sure that you won't go to jail. Yes, Tanner, you're getting this very, very precise. You almost get the entire picture. This is great. Okay, guys, since we already have someone getting very close, I'm gonna wrap up our discussion, and then let's just jump to the answer. What can we do to attack DS? Sorry, I'm just like looking at your guys' chat and laugh cannot stop myself from laughing. Okay, all right, back to our attack. We call this attack exhaustive search, just as Tanner said. So we want to brute force to find the key, and to be more formal, or say just like more precise so that we are on the same page, we're going to ask this question of, for a single message, okay, and is there possible to have two keys, K1 and K2, such that the encryption of the message given this using these two different keys actually is equal. Just like using different keys, the encrypted ciphertext is actually the same, and then the plain text is also the same. So this is not exactly that we're going to do for the attack, but I want to motivate you from this by this question first. So the answer is actually yes, because you can just like consider E as a mapping function. So it is possible. It's like hash collision. So although it is very unlikely, but still there is possibility that there are two encryption function. They just happen to collide for some of the message. So this is the reason why this could happen. But if we have many message, we have many pairs, this is going to be very less likely. This is going to be very unlikely to happen, right? Because it's very unlikely that you have two different keys, and then these two different keys manage to encrypt many plain text to the same ciphertext. So then the goal for us is that if we have some pairs, we have some pairs of the plain text and the ciphertext, then we want to find a key that can constantly encrypt and decrypt those pairs. And as long as we have pairs that is more enough, that is like, say, I will tell you some numbers later, but like as long as this queue is large enough, then we can get the right key, because it's unlikely that we have two different keys and it goes to the same result. Okay, so then given this fact, that what we could do for DS is that, suppose we have a message, all right? And then we are gonna, first of all, because this is block cipher, so we're gonna just cut this message into blocks. After we cut it into blocks, then for each of the block, DS will encrypt it and calculate the associated ciphertext, right? So in this case, then, for example, for this message, we're going to cut this 1 byte or so, 1 characters, because each of the block, as we just mentioned, has 64 bits, right? It must have 64 bits according to the standard of the ES. So this is 64 bits, 64 bits, 64. Okay. So after the encryption, we also have 64 bits. So the ciphertext is also 64 bits. And then for us, the goal is that find the key, and remember for DES, the key is 56 bits. I know this might be a number that is very counterintuitive because it's not 2 to the something. It's not an exponential number of 2. But anyway, this is how they works, how it defines. And actually, there was a trade-off of the length of key when the DES standard is made. But like now, it is what it is. So it is 56 bits. So the goal is to find this key such that the encrypted message for each of those above plain text will be equal to the associated ciphertext. And it can be for 1, 2, 3, 4, etc. Usually 1 will be enough, actually. So then what we're gonna do, as I said, very easy, just brute force, try all the different possibilities for the key. I saw questions. It says, what is MI? Oh, so MI here it is the MI. This is the message. So this is M1, M2, M3, M4. And then associated with that is C1, C2, C3, and C4. Okay, cool. So then we're gonna brute force, and it turns out that with fancy machines, brute forcing a 56-bit key is not very hard. So let's take a look at this timeline. This is the time, when we have good machines keep cracking DS. And as you see here, in the shortest time possible is 22 hours, which is quite fast. So that means that if you have a key, if you use DS to encrypt something, then someone can just like crack your crypto system within a day. Although that is a little bit expensive because it is distributed. But then looking at in year 2006, someone can spend 7 days, which is still not long because, say, for example, if you are say your army, you contact with other army, you want to, your soldiers are contacting with other soldiers, and then you use this crypto, and then you fix the key, and you probably won't gonna change it in a week because you're gonna make sure that you can communicate constantly. But then someone can only spend about $10,000 and 7 days to break your crypto system. They can know the key, they can know exactly that you're talking about, and they can forge you, they can impersonate you, which can be pretty dangerous. So this is how, I would say how bad, but just like how possible that, how likely that an attack can be launched and then crack a DES cipher. And as Tanner mentioned, the time complexity is 2 to the 56. And I would say the average will be probably 2 to the 56 over 2, because if you're lucky enough, you can only just try a half of it and you can get it. If you're not very lucky, you have to try the second half. But anyway, the time complexity will be in 2 to the 56 because you want to try all the 56 bits. Okay, so now I want to think about, given the fact that DS can be cracked by brute force, how can we mitigate this? Can we come up with something very similar to DS, but if someone's gonna use brute force to crack it, it's gonna take them longer time, like a time that is much longer than 2 to the 56, so that it is okay for us to accept brute force. So I saw the question in the chat asking that, is this the time, like this 2 to the 56, the time for a single Li value, or to find all? I don't quite understand what you mean by the L value, but if you're talking about key, then this is the time to find a single key. So it's like, if you know that someone is communicating with a specific key, this is the time that you need to cost to find the key. Okay. Right. I mean, technically, this is a wrong annotation. So I would say this actually, it should be O of K, and then K is 0, 1 to the 56. So, yeah. So basically here, I shouldn't use this notation of O, but you can consider that the time complexity as you need to calculate for 2 to the 56 times. Thanks for correcting, Tanner. Okay. So now let's keep thinking about the possible mitigation. So what kind of possible mitigation that you can have? If you want to make the brute force search expensive enough so that it won't be able to make it like within a reasonable amount of time. And Tanner says that bigger keys, yes, that's correct. So that's comes to this part, right? So if you have a longer key, then yes, you will have a longer days. What if we change the current crypto ways? Okay, so someone was saying, what about more Feistel functions? Even though there's more Feistel functions, the key doesn't change. If the key doesn't change, then brute forcing the key is gonna still take the very similar time because Feistel function doesn't cost too much time. Well, AES uses at least the 128, that's correct. But for DS, you know, I mean, 148-bit key also seems fine because 2 to the 72 is pretty long. But besides that, is there any other way to have a better design? I think we have discussed this for some time, so I'm gonna move on and introduce you a possible thought. And I would like you to think about whether or not this possible mitigation makes sense. Okay. So we call this specific scheme 2DS. This is called the 2DS cipher. So we define the cipher in a way that this is like an embedded DES. So you want to do DES for twice. Suppose that you have a plain text. Right? So this plain text is M. And you will have two keys. Each of the key is still 56 bits. So you're gonna do this, you encrypt for twice. And as Joshua said, you're gonna encrypt the message that is already encrypted. Okay, so if we're gonna have a scheme like this, so it's like a embedded DES, right? So I wanna ask you, is this secure? And if not, why? Can you come up with an attack that, will crack 2DS? Okay. It seems that you need some time to think, but we're running out of time, but that is fine. I'm gonna tell you the answer. So someone is saying try brute force again. So let's just try to brute force again. Okay. So what we could do is that first of all, this is this is the way that we could naively brute force it. So we're gonna try EK1 and EK2. We're gonna, for each of the possible K2, and then for each of the possible K1, we're gonna try if given a specific K1 and given specific K2, we use the encryption to encrypt the message. And then we're gonna check if this encrypted result is equal to the ciphertext, right? Then in this way, if it is equal, then we can more likely to be sure that the keys are K2 and K1. But if it's not, we just like keep moving on. Or say if we found this is true, then we can try another pair of ciphertext and the plain text and see if it still holds. So then how many times that we need to check? And remember that for DS, that is 2 to the 56 times. But then for this case, because we need to try both K1 and K2, then it will be 2 to the 56 times 2 to the 56, right? So that is equal to 2 to the 112. Okay, so if this is the case, then think about this. For 2 to the 56, you need, say, 7 days, or say 22 hours, right? But then for 2 to the 112, that means that you need 7 times 2 to the 56 days, or 22 times 2 to the 56 days, which is quite a lot. That is hours. So that means that brute force will be too expensive. What about the other possibilities? All right, so I'm gonna give you a hint, and then if you are interested to do this by yourself, you can continue to do it by yourself after I give you the hint. But if you don't, you can just listen to me to finish this entire attack. So we're gonna introduce a new type of attack. We call this meet in the middle attack. And this is a very interesting and very smart attack. So consider that you are gonna be sit in the middle of this 2 times of encryption, okay? And then if you looking at this starting from the middle, so it's here. And from here, if you're looking at this direction, then you have the plain text, and then you want to encrypt it. So you want to get a ciphertext. We call it C prime. And then if you look at this from the other direction, you are given ciphertext. And then for you actually want to go back, right? So you want to decrypt it. And we call this C prime prime. Or you can just say, actually, in this case, you consider this as a decryption. So it will be probably an M prime. And if you look at from the right-hand side perspective. But anyway, this is just a different of notation. I'm going to keep using C prime prime here. But I want you to know that this is just the I can't clear my notation again. Let me just keep it right now. Actually. So I'm just cross it. So know that we're going to use this notation. Then the goal for us is that instead of trying K1 and the K2, like in this like for loop, for K1 is equal to blah, blah, blah. And then for K2 is equal to blah, blah, blah. So this is like you multiply, you combine K1 and the K2. Instead of doing this in a combining way, we're going to try K1 and K2 separately. Okay, and that means that what if you generate this part first for different K1, and then you generate this part for different K2. Given an M, you generate all the possible C primes given different K1. That was a K1, 0, K1, 1, K1, 2, etc. And then for different types of, for different values of K2, you also generate that. Okay, so this is K2, 0, K2, 1, K2, 2, etc. So in this case, then can you make this brute force algorithm more efficient? And I want to think about this. Yes, I'd be looking for C prime is equal to C prime prime. That's correct. Okay, so let me just continue the slide. As Keenan, sorry, I don't know if I pronounced your name correct, but I hope I do. If not, please just let me know. Yep, cool, thanks. So as Keenan said, the idea is to find the equal situation, like find K1 and K2 at the situation that the ciphertext, the C prime and C prime prime is equal, it's the same. So in this case, we can change this algorithm in a way that we build the table. We build the table for K1 and for K2 and their different values. So we have the table for this part for the left-hand side first, and then we have the table for the right-hand side also. So this is the table. And then we want to find those values that are equal, right? So we want to find a match. And we can have a smarter algorithm to find a match in a way that we're just going to sort the table by the value, and then we're going to scan the table. And guys, just give me a second. Let me refresh my current annotation, and I'll be right back. Okay, so consider that we already have this table, right? And we sort it. And the way that we scan it is that we just start from the first one. And then we also start from the first one of the other table. And then we compare the value. Say, if this value is small, then let's continue. See if this value, because we already sorted, say we're gonna store this in a increasing order. So this is the smallest, and this is the greatest. So you just do this, you find that, okay, and to the time that this is equal or larger than this, and then you stop, right? And then you look at this cursor, start to move the cursor. And two, you find a position that you happen to find something equal. Okay, so in this case, I want to think about the time complexity, or say like the number of the number of checks, the number of times that you need to check for each keys. And also I want you to think about the space complexity. So question from the chat, do I have to search and compare P to the 56 result? I don't quite get what you mean by P. Let me know it and I will answer your question. Okay, you got it. That's nice. And then assuming you have a lot of storage, could you do it in 2 to the 57 and a bunch of searches? And that the answer is yes. And that is exactly the complexity analysis. So in terms of time, remember that if we're going to do this original brute force way, because we have to, for each of the K1, we need to try different K2. So that's going to be 2 to the 56 times 2 to the 56. So that is 2 to the 112. However, if we are going to use the same method, then we try each value of the K, and then we sort it using the quickest one, like a quick sort. And then we combine them together. And this is going to be much smaller than 2 to the 112. So we have a much faster way to crack this scheme. And also the space is just like approximately 2 to the 56, which is the table size. Okay, so this is the mid in the middle attack. And now we know that 2DS is not secure because 2 to the 63 is a reasonable reasonable number for the times of checking, and we can still crack it in a reasonably small time, like reasonably short amount of time. Okay. Then what about other DS approach? I want you to inspire from 2DS and then think about that. Can we make 2DS more complicated so that a brute force will not be able to crack it? Peter said 3DS and Emma says 20DS. That is amazing. So I guess 3DS will be enough, but also I'm pretty sure that 20DS will work as well. And let's take a look at 3DS. So the way that 3DS works is in the following way. So instead of like previously, we have only 2 encryptions, we're not gonna have insert a decryption in the middle. And then if we insert one more layer in the middle, even though someone's doing a in the middle attack, on one hand, like on one direction, he only needs to try for K3, but on the other direction, he has to try 2 keys. And that is gonna be complex enough for brute force. And in this case, the time will be approximately 2 to the 118. And the space will be approximately 2 to the 56. Actually, it can be larger. It will say times 2 because you have to have sorry. My mind doesn't work. You have to have 2 tables. So that's why you're gonna have 2 to the 56 approximately. Okay, so then let's make it a little bit more formal. For triple DS, let's just use E to denote the encryption. And this encryption takes key and a plain text. And when I say am here, it just means that the space of the plain text. And then it will output in the same space. Although we call it like ciphertext, but it's ciphertext and plain text, they share the same space. So I'm gonna just use am here. So then we define the triple DS, which we just use 3E to denote as the way that we have 3 keys. And then given a plain text, we're gonna encrypt it in a way that this is the encryption function for triple DS, and that is equal to the third key. Well, I mean, depending on which order you start to count, but here I'm gonna just use key 3, K3 over here. So you're gonna first encrypt it, and then decrypt it, and then encrypt it. So it's like 3 layers. Okay. Then for 3 DAS, for triple DAS, the key size will be 100, like three key, and then each of that is 56 bits. So the total would be 168 bits. And the issue for DAS is, for triple DAS, is that it will have to be 3 times slower, because every time for one encryption, you're going to do encryption, decryption, and encryption. So you're going to do this for 3 times. So it's going to be 3 times slower. But the good thing is that it is kind of resistant, or say it is too expensive for brute force, for exhaustive search, because in this case, then the time complexity would be about 2 to the 118. However, one thing that I want to be alerted is that you don't really want to make K1, K2, K3 equal, because if these 3 keys are equal, then you're literally just go back to DES, right? Because you just use the same key to encrypt it, and you decrypt the message and then encrypt it again. And you don't want this to happen. So you want to make sure that these 3 keys are different. And I was looking at the questions. Keenan was asking a very interesting question. What's the point of decryption instead of encryption for 3 times? Honestly, I don't know. I probably need to do some assignment, do some homework to look into this, to understand why it's using decryption. So I also encourage you to search. I'm pretty sure that someone has talked about this online. So just Google it and see if there is discussion about this. And I would like to know this answer as well. Let me know if you happen to, if you find something. Okay. So now I'm going to talk about another possibility. Like besides triple DAS, there is also another possible ways to design a secure, but still not that secure cipher, which is called DAS-X. So the reason why it's called DAS-X, because this is a combination of DAS and XOR operation. And here's the way that it is designed. We're designing, the encryption again as a block cipher, and it's gonna given the plain text. Sorry, remove this. Given a plain text and the key, it's gonna encrypt the key, encrypt the cipher. Encrypt the plain text to a ciphertext. And we define the encryption of DAS-X as EX. And then it's going to take 3 keys again. And then it's going to take a plain text. But then the way that they encrypt the plain text is that it's going to use the plain text to XOR with one of the keys. So this is a little bit like the stream cipher that we mentioned before. So we first do an XOR operation, and then we encrypt it, and then we XOR that with K1. And I want to note that if we're going to use DAS-X, then the key length will be different, because here we want to make sure that K3 will be able to XOR with AM. And if you still remember, the length of AM is 64 bits, according to DAS, right? So K3 has to be also in 64 bits. And then K2 still 56 bits. And then because we're going to do XOR again, and we know that the ciphertext is also 64 bits for a block. So here, K1 is also 64 bits. That's why that the total key length will be 64 plus 56 plus 64. So that is 184 bits. Okay, so now I want to think about how can we possibly exhaustive attack this approach, this scheme, this cipher. And I am giving this hint over here, but I'm not going to explain it right now. I want you to look at this hint and then think about how could you break the cipher. And Dean, you're in the right direction. I think you're getting it. You're right. K1 basically didn't do anything. And anyone else have more ideas? I'm gonna hold here for a second and let you guys think. I saw the discussion with Dean and Tanner, which is great. Okay, I'm gonna explain this. I know this is a little tricky to understand, so I will explain this first, and then if you still don't understand, let me know. I will try this again. The way that it works is that let's try the value of K2 and K3, but we're not gonna try the value of K1. So given K2 and K3, different values for K2 and K3, right? And then given an M, we're gonna get a value. So we're gonna get the value of, let me just write over here. So suppose that given M, and then for K2, some value, and then for K3, some value, right? I'm gonna put IJ over here. You know what I mean? So like for K2 is equal to some value, K3 is equal to some value, we can calculate the E of K2 and then M XOR K3. And also, since we also know C, right? So we can also get K1 is equal to C XOR this E value. So in this way, you get the value of K2, K3, and K1. Okay, and now what you're gonna do next is that now let's try another pair of M and C. Let's say this is M prime and C prime. Okay, so now what we're gonna do is still given K2 and K3, we're gonna calculate the other pair. And then we're gonna get another K1, right? And then we're gonna compare K1 and K1 prime. We wanna look at this two and see if they're equal. If they're equal, then it means that this is a good sign. It means that we almost get the result. But if it doesn't equal, if it is not equal, that means that we cannot come up with a combination of K2, K3 and K1 that can make this M and C and M prime and C prime consistent. So we want to move on from K2 and K3. We want to try other values. So in this case, we need more pairs of M and C. We probably need 2 or 3 or even more, but this is also same for the other desks, because to guarantee that we get the right key, get the right K for DAS, we also need to try for multiple blocks. So here we are also using multiple blocks, which is not like need more information or something. So it's just this will very interestingly to help us to avoid trying different values for K1, because K1 can be calculated. And the way that we detect whether or not K2 and K3 is correct is by looking at if K1's value is consistent. Okay. So for an exhaustive attack like such, what is the possible, like what is the number of times that you need to try? So because we need to try both K2 and K3, then we need to try 2 to the 120 times, because that is 2 to the 64 times 2 to the 56. Okay, and then I'm not going to talk about this, but it has a similar fashion. I want to think this offline. Given this type of exhaustive search, given that we know that K1 doesn't really do anything, then we can infer that if we design the crypto in this way, like the encryption is in this way, that won't help us to defend against exhaustive attack. I want to leave this offline and for you to think about that. All right. So this is everything that I want to discuss. I want to introduce to you about DES. And the rest of it is going to be very quick. I know that we also are running out of time. Just give you a quick overview for AES. I'm not going to talk about the details. So just let you know that because DES can be broken, and then like 3DS is too slow, then NIST wants a new proposal for block cipher, and you know, NES starts to come into play. AES is the winner, and usually, you know, right now we're still using AES quite prevalently. Usually there can be keys of 128, 192, or 256, and the block size is 128 bits. So AES is based on the idea of substitution and permutation networks. So instead of using Feistel networks, it has another different kinds of networks using substitution and permutation operations. And AES, so far so good. There's no practical attack as long as it is implemented correctly. And honestly, it's not very easy to make AES implemented correctly. And for more information, I would just encourage you to read the Wikipedia page. I know it's not professional to read Wikipedia, but honestly, when I look at the Wikipedia page for AES, I think it's quite detailed, and the content here are mostly correct. So if you're interested in more details about AES, I would like you to look into that. All right, and then that's pretty much for today. We're done with block cipher, the first part, and next lecture, we're going to talk about how to operate on multiple blocks. Thanks, guys. I will see you in the next lecture.
Thank you.
Thanks.